Hello, welcome to my channel. In this video, we are going to be taking a look at photoelectric effects. In this video, we are going to be looking at the photoelectric effects, understand it, and derive formulas that are associated with photoelectric effects. So let's go. So this is a diagram that describes the photoelectric effect. So we have the anode at this point. We have the cathode. There's a chamber that is filled with vacuum. And we have our voltage source. We have our rheostats. There's a galvanometer that measures the current that flows through the system. So at this point, we notice that when light falls on this particular plate, electrons will be ejected. And these electrons will definitely be attracted to the anode because this part is positive and this side is negative. So when electrons are ejected and attracted to this point, current will be established. So because current will be established, it's important for us to know that all the electrons that will be ejected at this point will all have different speed. Now, we're interested in the one with the highest speed. So the electron that will be ejected here with the highest speed, we're interested in it. Some we have the lowest speed, while some we have in between. Okay, so when the electron is ejected here, the one with the highest speed is ejected from this point. It gets attracted to this point with that same speed. And for us to generate formula to describe that phenomenon, it will be difficult for us to get formula to explain that concept. So what we can do is to reverse this polarity, where this part will now be positive, this part will be negative. In so doing, we are making this part negative and making this part positive. So when light falls on this same plate now, some of the electrons will be attracted to this, despite the fact that we changed the polarity. But what we can do is to adjust this to make the voltage, to increase that negative voltage between this and this. So as we keep on increasing it, a point will come where we will no longer have any current detected. At that point, what it means is that the electron with the maximum speed, as it is leaving this particular surface, before it gets to this point, it stops. So at that point where it stops, the potential needed to stop the electron with the maximum speed, the potential is called the stopping potential. So in this scenario now, we can use the conservation of energy to resolve the formula for that system. So we have the initial kinetic energy plus the initial potential must be equal to the final kinetic energy plus the final potential. So the initial kinetic energy of the electron with the maximum speed will be given as K max. The potential there, just because the electron is just about to leave the surface, will be 0. Must be equal to the K final. The K final, when the electron gets to this point, stops, so this part will be 0. While the potential here, because the electron travels from this point to this point inside that electric field that is established between this anode and cathode, will be electron times the volt. So we have this expression K max plus 0 equal to 0 plus our potential there, because we have reversed it, is supposed to take negative plus the negative electron, so it becomes positive. So we finally established our K max equal to electron volts. So where our volt here, V naught, is called the stopping potential. So we can also re-express this formula as K max equal to EV naught equal to half of mv squared maximum. Problem can come up where you are asked to find the maximum velocity, right? So now that we have established this, let's now go back to the light source. So when the light falls on this, it does work in digging electron from the surface. And once that electron is dug, then it possesses a speed with which it will be ejected from this point towards this point. And that light source possesses energy called HF, where our F there is the frequency, the H there is the Planck's constant. So that HF will be totally converted to the work done in it digging out the electron from the surface and converted to what kinetic energy that will be used to travel from this point to this point. So we have the formula as HF, which is the energy of the light, will be converted to the work in digging out the electron, plus the kinetic energy, that is the speed with which the electron will be ejected from this point to this point. Now this formula is for the electron with the highest speed or the maximum speed, right? So at this point, we notice that our Kmax can also be replaced with EV naught, since we have established that Kmax is equal to EV naught. So we now have HF equal to phi plus EV naught. So this is the other formula that we have established. Also, if you consider these lights with HF, we can have a situation whereby the frequency of that light is just enough to release electron from the surface, right? So if the frequency is not high enough, but it is just sufficient to dig out electron, that electron might just be dug, but might not have the enough velocity to be ejected out of this point. So at that point, our Kmax will be 0. This formula will reduce to this. So this frequency that you see here, which is called F naught, is lesser than this frequency. This frequency is just the frequency needed to dig out the electron. And because the velocity of that particular electron is 0, we have HF naught equal to 5. This F naught is called the threshold frequency or the cutoff frequency. Okay, and that reduces to HF naught equal to 5. So we have established another formula. But also, sometimes we might not want this formula, we want it in another form. So that gives us HC all over lambda. So HC all over lambda not equal to the work function. So we've established another formula. So HC all over lambda naught. This one is the cutoff wavelength or the threshold wavelength, which is equal to what? Phi, the work function. Sometimes when we're solving problems, our HC can be re-expressed as 1240 electron volts dots times nanometer, right? Sometimes when we need if the combination of these two, we can just use this particular expression. Okay, so now that we have established all the formulas needed to solve problem under photoelectric, let's summarize all the formulas again. So we have the first one is this, which was got from this one. The second one is this, which was got from this point. The third one is this, which is this. And the fourth one is this, which is this particular one. So these are the 4 formulas that you need to solve any problem in photoelectric effects, right? So let's take a typical example of, but also mind you, you can replace your HF naught with this one. You can replace this HF with HC all over lambda. You can replace HF with HC all over lambda. So let's look at a typical problem where we can apply one of these formula. So we have a monochromatic light beam falls on a target that has a work function of 2.2 electron volts. If a potential difference of 2.0 electron volts is needed to stop the incoming electrons, what is the wavelength of the light beam? So let's see what we are given. We have our work function, which is 2.2. The stopping potential is 2 points. And we have to calculate the wavelength of that particular beam. So let's recall the 4 formulas again that can be used to solve problems under photoelectric effect. We have it as 1, 2, 3, 4. So if you look at the first, they're talking about work function. There's nothing like work function here, so we can eliminate this. Then if you look at this, there's nothing like threshold frequency or threshold wavelength, so we can eliminate this. Then, if we also look at it, there is not like kinetic energy or maximum kinetic energy, so we can eliminate this. So we fall back to this particular formula. Now that we have this formula to use, we have it as HF equal to work function plus this expression. But mind you, our HF can also be replaced as HC all over lambda, where our HC is 1240, so on and so forth. So we have this expression. Our work function is 2.2 electron volts. Our electron is E times our potential, stopping potential is 2. If we rearrange this one by making this one proper, we have this expression 2.2 electron volt plus 2 electron volts. We can add this one to become 4.2 electron volts. So we have this expression. We can take this one to this point, bring this one back, and we have this expression. So electron volts can cancel this, 4.2 can cancel this, leaving our lambda equal to this formula. So we have this final expression as lambda equal to 295 nanometer, where our nano here represents 10 raised power minus 9. I hope this helps. Please like, share, and follow. Also, in our next video, we are going to be solving more problems on photoelectric effect where we can make use of any of this formula. Thank you.